talks on artificial intelligence and machine learning that are jointly sponsored by Metron and George Mason University. Today's speaker is Professor John Buck of the University of Massachusetts, Dartmouth, and his topic is Universal Adaptive Beamformers, Machine Learning Meets Array Processing. Now, a little background on Dr. Buck. He's a Chancellor Professor at the Department of Electrical and Computer Engineering at the University of Massachusetts, Dartmouth. He has taught at UMass Dartmouth since receiving his PhD from MIT and Woods Hole, an MIT Woods Hole joint program in 1996. Professor Buck is a fellow of the Acoustical Society of America and a senior member of the IEEE. He has numerous teaching awards, including the Manning Prize for Excellence in Teaching from the university and Teacher of the Year Award from the UMass Dartmouth Faculty Federation and the Goodwin Medal from MIT. Professor Buck is a past recipient of the ONR Young Investigator and NSF Career Awards, as well as a former Fulbright Senior Fellow to Australia. He has held visiting appointments at numerous places, Woods Hole, Sydney University, the Australian Defence Science and Technology Organization, and many other, including University of St. Andrews. Sounds like maybe a place you might want to play golf. So Professor Buck is the co-author of the Signals and Systems Concept Inventory, in addition to 2 signal processing textbooks. His research interests include array signal processing, underwater acoustics, marine mammal bioacoustics, and engineering pedagogy. Professor Buck.
Thank you, Larry. Again, I'm John Buck. Thank you for that great introduction. I'm going to talk to you today about Universal Adaptive Beamforming as a research project I've been working on lately. I thought I've really enjoyed some of the earlier machine learning talks in this seminar series. One of the small silver linings is getting to attend remote seminars like this and see things I wouldn't have seen. So I thought this work might be a really good fit for this seminar series because it brings together array processing, which I certainly know there are people in Metron who are very focused on that, and that's an important part of Metron's business, with the focus on machine learning. A lot of what I'm going to present to you today was done in collaboration with Professor Kathleen Wage from George Mason University, who I think is going to join us, and Andy Singer from the University of Illinois Urbana-Champaign. And all this work was supported by the Office of Naval Research, code 321 US. Before I jump in, the big picture on what I'm going to talk about today comes from problems in practical beamforming. There are a lot of times when we go out with passive sonar arrays and we know in theory what the optimal solution is, but it involves parameters we don't have access to in the real world in real time. And so they're often, this is sometimes called regularization, or the other technical name for it is the special sauce. So sometimes we need to find these things. And if I gave you a bunch of recorded data, you could go off and process that data like in batches, and by trial and error, find the best regularization parameters for it. But that's no way to, you can't drive a ship or fly an airplane in that mode. You need, what we really need would be to have some causal online algorithm that learns and adapts as it goes to find these regularization parameters in real time. And so that's what I'm going to talk about today. That turns out the trick to doing this brings together some of the adaptive beamforming ideas with ideas that are familiar in machine learning. Now, when I started putting the talk together a couple of weeks ago, I had a short phone call with Bob Zarnich, and he did tell, in terms of talking about audience, told me not everybody wakes up thinking about array processing every morning the way I do. So I'm going to do like an overview for about 20 minutes, getting the array processing issues familiar to the people who are more focused on machine learning, so you have some basic idea of where things are coming from. And then at that point, we'll pivot and say, now that you understand the context, let's see the part where we get the machine learning chocolate dipped in the array processing peanut butter, as it were. And that's about the point where someone probably will need to wake up people like Roy Strait and Christine Bell to tell them I'm going to say something they don't already know, probably. But I will tell those people. Yes?
Could you record your talk, please? Because
you're the host now. I
can't record. I can't record because you're the host now. I made you.
Oh, because I'm the host now, right? Where did the record? No, that's remote.
At the bottom.
It says, well, it says if I push a button, I'll stop recording. Is it recording already?
It's not on my, I can't record it because you're the host.
Oh, because I think.
I think it's recording.
I think you're good, John. Just
Am I good? All right.
I'm seeing that it is being
Yeah,
recorded.
yeah. On the status bar, I see the little red light blinking like it's recording. So I think we're good with that.
Okay.
So, all right. All
Thank
right.
you.
So now that we're good with that, moving ahead. So the outline, I'm going to talk a background on narrowband adaptive beamforming, and then universal adaptive beamforming is where we combine ideas from machine learning and maybe a little bit of information theory to get the new results. I will show you some simulations that show the value of these, and then some mostly experimental real data results from the Philippine Sea experiment. This was work done in collaboration with Kathleen also. So to start out, we're going to focus on the simplest example of an array today, which is a uniform linear array. It has all the main ideas we're going to need for that, and the idea that we're trying to measure a plane wave coming in across it. And so if I have this is my plane wave front here coming in, it will strike one sensor and then another and another. And there'll be a time delay as the wavefront gets from sensor to sensor. And that time delay depends on how far apart the sensors are, the speed of sound in the medium, and the cosine of the angle the signal's coming from. But that time delay is the physical thing that is embedded, like where the information about angle is embedded, is that relative time delay from sensor to sensor. And just to call attention to the state of the angle is defined relative to the axis of the array. So theta equals 0 is what in the Navy world we often call end fire. Theta equals 90 is broadside, the way this is defined. And to satisfy the spatial Nyquist theorem and avoid aliasing, we need to assume that the distance between the sensors is less than or equal to half a wavelength. And so to show you what this delay looks like as the signal comes across the array, here's sort of another cartoon of a 4-element array. And as the signal comes in, I'm showing here's the same pulse and a plane wave arriving at each sensor, but it's slightly delayed at each sensor, shown by the slope of this red line. So that's the big picture concept, is that delay, the slope of that red line, that has the information about the angle of arrival to it. And so we're going to sort of talk conceptually about that first, and then I'll show you the sort of mathematical formula of it. So when I want to beamform, work with an array of sensors, what I want to do is figure out how to shift and scale the sensors and then add them together to get a single output. And so for this very simple case, the main thing I need to do is if I have some hypothesized direction the signal may be coming from, informally, we often call that the look direction. I work out, well, what would be the time delay for that look direction? And I'm going to shift each signal to the left by the right amount for that direction so that any energy coming from that direction is all lined up. And then when I sum down vertically across the sensors, I get constructive interference and I reinforce the signal from the direction of interest. If the signal, on the other hand, if the signal is coming from some other direction, those shifted signals won't line up and I'll get some mixture of maybe destructive interference, or at least not fully constructive. I'll have some attenuation of the signals from other directions. And again, this look direction time delay has the same relationship between the distance between sensors, speed of sound, and the directional cosine. So that's, there's a lot of math you can get lost in array beamforming, but the main idea, one of the main ideas in beamforming, always to keep in the front of your mind, is we're trying to set up constructive interference from desired directions and get destructive interference from all the other directions. So now we've covered that big concept. Let's see, well, how does that look when I actually put equations to math to the equations? And so when I have narrowband signals with a single frequency, I can represent them by a vector of complex phasors. And so if I think of P sub n of t as the time trace I'm seeing at the nth sensor, like the pressure wave, and it's this common pulse x with a different delay as I move down the sensors, I can use my razor sharp knowledge of Fourier transforms and say, well, if I'm delaying things in time, that means I'm multiplying by a complex exponential in frequency. So that gets this phase term up here appearing. And now we say, well, if we want to simplify this and clean it up some, we say the time delay has that expression we just showed. I plug that in for tau, use a few wave identities to simplify 2 pi f over c is the wave number k. And then assuming I have a narrowband signal and I've sampled rate at lambda over 2, k times d will leave me with just a pi here. And so what this is important about this equation, it's saying when I think about the Fourier transform of each successive sensor, they have this common factor, the Fourier transform from the pulse that's being transmitted, and then a different phase for each sensor this vector of complex phasors for each sensor that represents the structure, the spatial structure due to the angle of arrival, which is hidden here in this U, which is the cosine of the angle. And so I can represent my array data for a single frequency or narrowband signal by saying, well, I've got some amplitude due to the transmitted pulse, and then this vector of complex phasors, which basically is saying, if I know the frequency of the signal being transmitted, I don't need the whole waveform. All I need to know for that frequency is what's the magnitude and phase to get the time shifts right. So that's the equation for the pressure side. If I now look at the beamforming side, we say, well, I'm going to make my output, like we said a minute ago, by shifting all these pressure things, possibly scaling by some amplitude, and then adding them up, trying to create that constructive interference. And so because we live in a merciful universe, the Fourier transform is a linear transformation. And I could take the Fourier transform of inside the sum just of each term, and I get the same frequency shift property just with the opposite exponent because I'm shifting in the opposite direction in time. I now plug in for my look direction, my time, and do the same simplifications. And I end up down here with something that says, I've got, again, that common factor out front due to the pulse being transmitted, and then a sum based on the array weights if I'm using them. And then this complex exponential that basically comes down to the difference between the true direction of the signal U and the direction I'm looking in, U naught. And so if these two are equal, this difference will be 0. If I'm looking in the right direction, that difference will be 0. And so when I add e to the 0 up, that's 1. And so I'll be adding up real numbers, and that's what the constructive interference looks like. And the nice thing about formulating it this way is I can define a vector W for the look direction that are these coefficients. And then I say this beamformer output, then the narrowband beamformer output, just turns into an inner product of two complex vectors, one for the array weights, which are essentially the coefficients of my spatial filter, and the other for the observed data. It's also worth highlighting for this series that this is like a point of tangency with machine learning, right? There are a lot of things in machine learning where we say, I'm going to take an inner product of a weight vector with some observed data. So for those of you that are more used to the machine learning framework than the beamforming framework, this is an idea you should find comforting and familiar, this idea that I'm going to take some observed data and then multiply and sum across a weight vector, and I'm trying to find the right weight vector for some task. Okay, and then the question is, well, how well does an array do it, keeping the things I want and rejecting the others? Well, we use the beam pattern as a way to characterize that. The beam pattern is for a spatial filter what a frequency response is for a classic time domain filter. Remember, in a time domain situation, like in your undergrad signals class, or maybe a DSP class you had, a frequency response will look at a given set of filter coefficients and say, for each frequency, what gain will be applied as it goes through the system. A beam pattern is answering a similar question. It's saying, for this beamformer, what gain will I apply to each angle of arrival? So on the x-axis here, I have the cosine of the arrival angle. So this is cos theta equals 0 at 90 degrees. And so it's saying if my array weights look like this and I compute the beam pattern, I'll have a gain of 0 dB. That is, in linear terms, that's a gain of 1. And we call this the main lobe. Frequencies near here, or plane waves from that direction will come through unattenuated. But these side lobes are showing things are 13 to 15 dB down. Energy coming from these other directions will be attenuated. And then just like we see in a classic DSP sense, this is periodic because we're sampling with the array, we're sampling in space. That creates periodicity and angle. But if I want to change the array weights, I can steer to different look directions. So if I want to steer this to look here at this would be 30 degrees away from the array angle, or 60 from broadside, I would put a different set of coefficients in here, and the beam pattern has shifted. But it also shows one of the advantages of working in the cosine space rather than just angle, is this is a true shift. Nothing is distorted. It's very like the modulation properties we see in DSP. So when we've steered it by just changing the phases, we've created the constructive interference in a different direction. So that's the basic idea behind what we call conventional beamforming, or sometimes called delay in sum beamforming. So let me show you a practical example. When we were working on the Universal stuff during my sabbatical at Urbana-Champaign, Andy Singer and I got in a lot of bike rides. In fact, we did a lot of signal processing where we're out on or thinking about ideas on long bike rides. And one day we came to this very strange looking stop sign, and we both were looking for a minute saying, what's going on? And then we said, oh, that's a spatial filter. And to help you understand what is going on here with spatial filtering, let me show you a map of where we were. This is sort of west of Champaign, Illinois. We were coming on this little side road, Bluebill Road, about to merge onto a heavy surface road. This is a big sort of wide open prairie plains, 55-mile-an-hour, 2-lane road coming into Champaign. And so the problem here is if you were on the little side street, you definitely had to stop before you got into the big traffic here. But at this very narrow angle, people coming on the main road would think they had the stop sign applying to them too. And so the local highway department had created this mechanical filter that said, if you're on Bluebill Road, you're in the main lobe of this mechanical filter. And so you're seeing the stop command, and it's being transmitted through to you with a full gain of 1 or 0 dB. But as you move to the side, oh, wrong way. As you move to the side over towards the major road, you get into the side lobes, and the message to stop has been filtered out. And so this is sort of a good physical intuition about what spatial filtering is trying to do with sound, the way this does with the command to stop, and only from certain angles does the stop sign tell you to stop. Okay, so that's the conventional beamforming. I've shown you what it is. Let me show you a little bit about why we need beamformers, or why we use beamformers. So again, back to a simple linear array. In real life, unlike the pulses I showed you that were nice and neat before, even when I have a signal coming from a certain direction, which we represent again by this phasor that we call the replica vector that captures the angle information, it's going to have a time-varying amplitude. And so we say that we model that as a random complex Gaussian with a random magnitude and phase. And because the world is what it is, we have noise as well. So we're often trying to estimate where the sound is coming from in the presence of a varying amplitude and noise. And one of the most basic tasks in array processing is saying, can we detect something? When are we just observing noise? And when are we seeing a signal plus noise? And so this is, I'm going to show you a series of examples. And actually, I flagged this first one is from a talk Kathleen and I worked on together, but she created this example to help make real the benefit of the array processing. So we're going to show an example where there are 200 measurements, where we call snapshots, often in the sonar world. And the signal turns on after 125 measurements, but it's relatively weak. The power is a half, whereas the noise will have power 1 when we add it in. So we'd say the SNR is 10 log times the ratio of the powers. So 10 log of a half is minus 3 dB. So we'd like to be able to detect this change at 125. We're going to often look at these things on a log scale. So that same signal looks more like this. And to make it clear what the problem is, imagine now when I put the noise in, I can see that there's not going to be a big dramatic difference here, because the noise, if anything, is slightly higher than the signal. So if I'm just looking at this blind and I don't have helpfully colored signals, I may not see the change at 125. So let's see how we benefit from the conventional beamformer that I just showed you if we move and sum things to make coherent sum. So if we steer at we're going to take our observed pressure data represented as those complex phasors, take the inner product with a look direction where we're going to choose the beamformer to be where the signal's coming from. Normalize this is the number of sensors so that we have an overall gain of 1. And so we can find the output power in this quadratic form. In the interest of time, I'm not going to go through the whole derivation of where this comes from, but these are the array weights. And this is the covariance matrix, which is the matrix of all possible pairwise correlation between sensors of the array. So that has elements or units of pressure squared or voltage squared, depending on what you like, which explains how we get the power from it. And when we go through all this with the beamformer, we see when the dust settles, we have the power, the expected output will include the desired signal. That comes through with a gain of 1 like we'd like. But the beneficial thing here is that the noise power has been reduced by the number of sensors. And we call this the white noise gain. Hopefully, if you remember 1 or 2 things from your probability or array signal process or random signals classes, it will be that when you average uncorrelated random variables, you reduce the variance by the number of terms in the average. And so in addition to these shifting things going on to create constructive interference for plane waves the way we want, the other benefit we get, there's sort of 2 main benefits from processing an array of sensors. One is the spatial filtering with the constructive and destructive interference for desired and undesired directions. The second gain is that we reduce the uncorrelated component of the background noise by the effective averaging of this. And so we improve our ability to see the signal we want by pushing down the noise variance. So if I look at a single sensor, my signal coming in looks like this, and there's no obvious change at 125. But if I look at the output now, I see that the noise has been greatly reduced. And so because that noise has been suppressed, I see this big jump shift at 125. And so I can easily imagine making a detection system with a threshold that would notice that change and say, hey, there's something here now that wasn't here a second ago. So that's pretty easy, but in the real world, it's not usually just one signal and an interferer we're looking at. We're often looking at dealing with an interferer. And again, to come up with a practical example that help some of you relate to it. Some of you may have just hypothetically had the experience that if you have had the experience I've had, Christine Bell will say a lot of smart things, but she's not always as loud about it as, say, maybe if you're in the same room with Bob Zarnich at the same time, right? So Bob Zarnich might be rattling on about something, and I'm having a hard time trying to hear what thing Christine is saying, but realizing based on prior probabilities, it might be more important to hear what Christine is saying. And so you can imagine the blue signal here is Christine, and this is Bob Zarnich at a different angle coming in. And so now my measured data has both the thing I want and an interferer. And in this example, the interferer is going to turn on sooner. And so this is going to show us why conventional beamformers don't solve all of our problems. The question is, will we still be able to notice this quieter thing coming in 50 samples later? And so as Larry warned you in the introduction, one of my other interests is engineering pedagogy. And I have learned from that 20 minutes is about as long as I should talk without breaking things up for an exercise or questions. And so we're going to do a version of something I do in class a lot, even remotely, called a think, pair, share exercise, which is, I'm going to put up a question again that Kathleen and I worked on together. And I want you to think privately for I'll give you about a minute for your answer. We're going to do the truncated version today. That's just think, share. I was going to put everybody in breakout rooms of 2 people, but apparently the breakout room controls are not the same here as I would have in my academic version of Zoom. So we won't do the pair part where you normally get to argue with a partner about whether you agree, but we will do the sharing answers with a larger group. Though if Kathleen is here, she's disqualified because she knows the answer already. So here's the question. So assuming the interferer is much louder than the signal of interest, you have an array of 50 sensors. Again, that signal power is a half. The cosine of the angle for that is 90 degrees, so the cosine is 0 coming from broadside. The interferer is 10,000, power is 10,000, so much, much, much louder than that quiet thing we're looking for. And it's coming from an angle such that the cosine of that angle is 0.06, and the noise has the power of 1. And then on this side, you have the beam pattern on a log axis, so vertical axis here, and some of the part of the beam pattern you need for this problem going as the cosine goes from 0 to 0.2. And so I want you to look at this and based on this, make one of 3 conclusions. That you can look at it and say, well, this beamformer has a gain of 0 dB at broadside. So it's steered at broadside, so only the signal at broadside will come out in the output. You could say, well, the interferer will have some effect on the output, but I'll still clearly be able to see the source show up. Or option 3, the interferer will mask the source signal in the output. So I'm going to, again, take a minute just to think on your own about that. I'll start my watch here and use that to get a sip of tea while you all think, and then we'll come back for the share part of the exercise. All right, about 10 more seconds, then we'll go into share mode. If I'd been a little more organized, I would have created a poll to do beforehand for anonymous polling. But all right, so it's been a minute. Any brave soul want to put in the chat window their choice between 1, 2, or 3?
I can say it if you want.
Yeah, sure. Go ahead.
Number 3.
Number 3. Why did you pick number 3?
Well, it's going to be lowered by negative 13 dB because of the side lobe, but it's already almost 60 dB. So it's going to be 57 and 0. Broadside is going to go without interference, but it's very low to compare. So it's going to be way much higher than the actual signal.
So there's one theory for voting for number 3. How about who else? I thought I saw some other people I know here who had might be. Is John Gebby here? John Gebby's here. John, did you agree with that?
Hey, John.
Hey.
Yeah, actually, can you hear me okay?
Yeah, I hear you fine.
Yeah, that I would agree with that. Yep.
Yeah,
that reasoning with 0.06 looks like it's right in the side lobe.
Yep. No, that's exactly right. So I'm sorry, I didn't get the name of the first person. I don't think I know. Who was that? Who spoke up first?
Yazam.
Oh, yes. Nice to meet you. So yeah, Yazam's right is right on target. You can look and say, well, for each signal, I'm going to look at the gain here. So this will come in at minus 3 dB, have 0 dB of gain, so it's still at minus 3 dB. This one turns out this is, if you count the zeros carefully, it's 10 to the 4th. So this is 40 dB. It'll be lowered by 13 to 15. So it'll come down to maybe 25, 27, but still be much, much louder. So let's see how that actually plays out when we look at the signal here. Oh, wrong button. So now if I look at, here's my single sensor, you see the interferer even in one sensor because you see it jump up to 40 dB here. But I don't see any change at 125. That soft signal turning on isn't visible, and it still isn't visible here for exactly based on what we just heard. Option 3 says you're overwhelmed. Oh, and so here's actually the explanation again. Oh, wait, no, wrong way. Is that we look at what I just walked through. The power comes through with a gain of 1 for the desired signal, but we need to find something better than a conventional beamformer to get rid of the annoying interferer, the Bob Zarnich, if you will, in our, well, we don't need to get rid of them. We just need to dial it down a little bit. I don't want to take this too far, but so that brings us to adaptive beamforming, which is how do we say, one way to think of it, we say, well, if we'd been luckier, this red line would have fallen in the notch and been really attenuated. And so adaptive beamforming is about, we're not going to wait to be lucky. We're going to figure out how to bring the notch to the interferer to get rid of it. And so in 1969, Capon came up with the minimum variance distortionless response beamformer. So we just passed the 50-year anniversary of that, which sort of got lost in the shadow of the 50th anniversary of the moon landing. So while there were a lot of PBS specials about the anniversary of Apollo, we did not get the PBS special on the anniversary of adaptive beamforming, even though I think we have built way more adaptive beamformers in the last 50 years than the number of people we've sent to the moon. But I'm not bitter about that. We'll move on from that. So we're going to choose, what Capon said is we want to design a beamformer to choose the weights as a constrained optimization problem. We want to minimize the output power, but adding the constraint that I have to keep the gain of 1 in some desired look direction, right? So I can't just push the power to 0. I say anything coming from that look direction theta naught, I need to solve that so that I keep the gain as 1. And that's a nice Lagrange multiplier problem. You can set up in solvent, you get an expression that looks like this, that it's the inverse of the covariance matrix times the look direction vector that's sort of rescaling it. And this term here is just basically to get the gain to be 1. The real action in terms of constructive and destructive interference and scaling is this part over here. And so again, this is our covariance matrix. This is the look direction. And so this is sort of a different way to come up with the weights based on the noise. But if there are loud interferers present, this inverse covariance matrix will attenuate them. And so I keep hitting the wrong button. All right, so now if I look at our same example, again, our single sensor said I was in trouble, but now if I plot the black one with MVDR here, this is what the conventional beamformer got overwhelmed by the interferer, but the MVDR beamformer isn't. It's keeping the power low, and then I do see that desired jump at 125. I see a clear change. And so in theory, this is what I was talking about in my introduction. we know exactly what we want to do here, but we have a practical problem is in the real world, I don't know the covariance matrix of where all the things are and how loud they are. So I have to replace sigma with the sample covariance matrix S. And so we do whatever we do in the real world when we're stuck not knowing some theoretical thing, we rely on our old friend, the law of large numbers that says, well, if you can average enough of that thing, it ought to get close to the expected value. And so we collect a whole bunch of data, again, called snapshots, and say average all of them. And we're going to assume that sample covariance matrix S has an eigen decomposition like this, because we're going to be talking about that in a second. So let's see how that works. If we plug in to our beamformer with the estimated data, I mean, this disappointing answer is just doing that directly does not work all that well. That gives us this pink line here, which does not show a clear detection at 125. And this is for those of you who are used to thinking of such things, this is with 2 snapshots per sensor. We still see that there's not enough array gain, and the beamformer doesn't estimate very well. So there's a very clear difference between the pink magenta line and the black line, where if I knew the true theoretical thing, and then if I just had the average in this case of 100 snapshots for the 50 sensors. So why doesn't it work? Well, it turns out that average has problems with the noise eigenvalues. That my truth looks like this. I have a loud eigenvalue for the interferer, and then the background should be nice flat white noise. But if I just average 2 snapshots per sensor, I get the loud eigenvalue very well, but this thing that should be the flat red line has a really big slope to it, and I get a lot of very small eigenvalues here. Those are a problem because when I go to invert that matrix, inverting small things makes them really big. So these are going to turn out to be gains that amplify the background noise much more than I want, and that's going to destroy my beamformer's performance. So you say, well, maybe instead of like just leaving this alone, we should find some way to apply a constraint and say, what if we assume that background noise is white? And when you do that, you've essentially got to what's called the dominant mode rejection beamformer that was proposed by Doug Abraham and Norm Owsley in 1990, where they said, let's take that sample covariance matrix and break it into 2 pieces. We're going to keep one piece with the large eigenvalues because we're doing well at that. We're going to leave that alone. But the second piece with all the small eigenvalues, we're going to replace the actual eigenvalues by their average. So we're going to make it be constant, flat in that region. And we're going to impose that constraint on the data just by averaging, again, the n minus d smallest eigenvalues, and then still use the MVDR formula. When we go do that, we get what's shown here in the light blue line, which is almost indistinguishable from the theoretical MVDR. So that turns out to be a really good problem, a really good approach to force that background noise to be white. And I could go on more about that for a while, or maybe we can at the end of the discussion. I'm not now about why that's a good idea, but it does leave us with a different problem. And for those of you who have been very patiently waiting, now we're getting to the machine learning part of it, is we have essentially a model order selection problem, which is, keep doing that. We have a model order selection problem, which is how do we decide where to segment this sum? How do we decide this D effectively is saying, I need to know how many interferers are present that you want me to cancel out. There's a little bit of a mathematical footnote to that. I'm saying that because Roy's here and I don't want to get lost in that alley. But most of the time, what you're saying is how many interferers are here. And I need to know that somehow to find the right value to get this to perform. And so I've got a model order problem here, and that's what gets us into the universal adaptive beamforming. All right, so this is where the machine learning comes into play, saying, well, how do I figure out how many interferers are present? So let me say a little about universal algorithms. Universal algorithms are things I first learned of from information theory applications like source compression and prediction. A universal algorithm is a sequential, or sometimes called online algorithm. So it's not batch processing. It's got to be single pass through the data, something that in principle can be implemented in real time. It's an adaptive algorithm, which in fact, one of the early versions was called doubly adaptive by Ryabko. And this is very important. It converges asymptotically to perform as well as the best algorithm within a set of algorithms for every input sequence without having to assume a probability distribution. So it's sometimes called individual sequence convergence. So it's not about converging on average to be very good or converging with high probability. It's for every input sequence within a class, without assuming any PDFs over it, you can get very good performance. The example most of you probably use without knowing it's a universal algorithm is the zip compression algorithm. Zip can actually, if the file size is big enough, asymptotically, it can compress any file as well as the optimal Huffman coder that knew the PDF of that file. What got me interested in was on the prediction side in 1999, Andy Singer and Meir Fetter did a paper on universal linear prediction. In linear prediction, one of the common problems is I want to predict the next, well, linear prediction is about saying I want to predict the next value of the sequence as a linear combination of the previous values, but they have the model order problem. They say, well, how many of the previous values is the right number to use? And so by using this universal approach, Andy and Meir said, well, we can find out a doubly adaptive algorithm to do that. And that got me thinking in 1999, there are similar problems in beamforming. There ought to be ways to bring these ideas out of info theory and prediction problems into beamforming problems where we have similar model order problems. Full transparency, I then spent almost 2 decades failing to figure out how to do that with various levels of I wasn't working on it full time, but at various times working fairly intensely at ways that didn't work to create universal beamformers until that sabbatical in the fall of 2017 when I went out and Andy and I worked on it in a very focused way. And with the benefit of that and all the dead ends I'd already wasted or gotten discarded, we were able to get somewhere. So that's what I'm going to show you now. I need to figure out why. Oh, I bet I know why that's happening. I bet it's in here. I'm going to try that. So now, yeah, so that's what's going on. All right, I'll try to avoid hitting that. All right, so again, where we were when we finished adaptive beamforming story, Roy and Christine and other beamformers should wake up now. I'm going to get to the new part. The fundamental challenge for a DMR beamformer is you need to know the subspace dimension, which is loosely speaking the number of interferers in the environment. And so if you think of that algorithm I just discussed, you start with a bunch of observed array data snapshots. You average it to get a sample covariance matrix. You take an eigen decomposition, and those eigenvalues and eigenvectors, along with the replica vector, go through the DMR algorithm, which assumes it knows how many interferers are there to get you the set of array weights. That is the scaling and shift you want to apply to your sensor data to get to the output. So again, in one sense, this is also kind of adjacent to machine learning in the sense of I'm going to get a bunch of data and train something based on some hyperparameter to figure out what set of weights I want to take an inner product with my new test data with. So from that sense, beamforming shares a lot of DNA. Adaptive beamforming does share DNA with machine learning in that sense. But what I'm going to say is rather than assuming we know the right value of D, I did it again. I should just put a brick over that arrow. Rather than assuming we know the right value of D, what if we ran all of them in parallel? So I said, well, what if I run the beamformer assuming there's 1 interferer, 2 interferers, up to some maximum number M. I'm going to run them all in parallel. Each one will give me a slightly different set of array weights. And so at first glance, you might say, John, that's not better, that's worse. A minute ago, I had to guess some value of D and live with it. Now you're making, I've got M different array weight vectors, each of which have N sensors in them. I've got more things. How do I figure out what to do with my data? And the answer is you make a blend. You take these things and you combine them with a set of coefficients that are between 0 and 1 that all sum to 1. And so the set of weights you make are a blend of these weights here. And so rather than picking one array weight, you're going to you can think of this as a beamformer hedge fund. You're going to invest mu sub M in each of the different sets of array weights based on past performance. And there's really only one thing I'm aware of that's similar to this is Christine Bell solved the Bayesian problem that was more focused on when your look directions were on a different grid than where the signals were actually coming from. But her Bayesian beamformer came up with a similar structure that had this weighted blend of different beamformers in it. So it has, if people are familiar with that, I wanted to mention that because that may help orient you. It's very similar to Christine's work in the structure you get, but I think I'll show you some different interpretation and performance ideas than the way Christine set up the problem. So when we do this, the challenge we have is saying, well, I want to blend these things based on performance, but I don't have access to ground truth the way predictors do, or maybe in a machine language vocabulary, prediction is an interesting problem in the sense that your data is always labeled with a latency of 1. That if I'm trying to look at a predictor and say, well, which of these competing predictors are doing well, the answer is wait one sample and I can tell you, because I'll get the value, the next value, and then I'll compare them and do a mean squared error. So with a delay of 1, I always know where things are or how well things are doing. In the beamformer case, I can't say that. In the beamformer case, nobody says, okay, now that you got the measurement, we're going to stop the world and tell you what angle everything was at and how loud it was at. So we need to come up with a different approach to weighting the beamformers. And this is the thing that I struggled with for a lot of that time. And what's the right sort of unlabeled data equivalent or blind feedback version of figuring out performance. And then it turned out once I saw the problem the right way, it was simple, as it often is once you see it the right way. And Capon had the answer all along, which is that the beamformers are trying to suppress all the background power and interferes. Whoever has the least output power is doing the best job if they all have the same unity gain constraint, right? So to dig into that a little more, assume I have two weight vectors, A and B, that have the same unity gain constraints. They both have a gain of 1 in the same direction. So whatever power is coming from that direction, whatever, say in my earlier analogy, Christine is saying is a fixed gain, a fixed power. All the beamformers are going to have that much power. What they're competing on is then their different approaches to nulling out all the other interferers in the background and or suppressing the diffuse background noise. And so we can define our loss function in this comparison to be the total output power over time. So this is the magnitude squared of the beamformer output at each time. I just keep a running total of that. If this total is less for beamformer A than beamformer B, then right now A is a better beamformer for this data. And so I want to set up my blend function, those mu weights, so that A contributes more to the blend than B does. Right. And so in order to do that, we say, well, what's the right way to define those mu's in terms of the losses? Now we get to the real close connection, which is it's a softmax function. So again, something that shows up all the time in machine learning for looking at classification problems or multivariate classification problems, is this idea that you want to have e to the minus some performance parameter divided by the sum of that over all the options, right? So this normalizes, this denominator is just normalizing to make sure the sum is 1. And so if I look at the numerator, we say a beamformer that's performing well, we said we'll have a small loss. So e to the minus small thing will be relatively large compared to the other terms. So that will get a large value of mu. And so with the large value of mu, that will get a heavier investment or heavier weight on it and the overall blending of the beamformers. On the other extreme, if a beamformer doesn't have enough degrees of freedom and it can't cancel the interferers, this loss function will get quite large, and e to the minus that will go to get small very quickly, and will very quickly attenuate that beamformer and say, you know, you're not doing well. We don't want you as part of the mix in our beamformer in determining our output. And so we end up with a structure that looks like this, that I'm taking my array data. I have m competing beamformers, each of which give me different weight vectors. And then I'm looking at the performance of those with the softmax function to get these blend coefficients. I guess another name, I should have mentioned this a minute ago for this in the machine learning vocabulary, is sometimes these are called ensemble methods or mixture of expert methods. And these mu's, I think, are sometimes called the gating functions or the gating coefficients. So that may help some of you put this in context, that we're sort of gating these different beamformers by a certain amount to get our universal array weights. And then these are what we apply to the data to look at the performance. So here's the payoff in performance, which is I think what the information theory perspective brings us, is to say, if I've got m different beamformers that all have the same look direction, but they're competing in other ways, and I also put an upper bound on the magnitude squared of the weight vector, which we generally do for the sensitivity anyways, then if I look at the total output power for the loss, the universal beamformer, that the per sample average of the loss will be less than the smallest of the per sample average of all the competing beamformers in those parallel branches, plus a penalty term that goes like 2 times some constants over the number of samples. And so this right here, this min is saying, this is the one I would choose with 20/20 hindsight. If you let me go away and try these m different options and come back and pick the best one with 20/20 hindsight, I'm telling you, moving forward in real time, the universal algorithm can get arbitrarily close to that on a per sample output basis, because as n goes to infinity, the number of data samples, this term is going to vanish. And that this is true for every sequence of observations with finite bounded power. And so that, again, not assuming like X is Gaussian distribution or Rayleigh or anything, but for every individual sequence of observations. That's a very powerful convergence result that we get from sort of melding the info theory universal prediction results into this beamformer / machine learning framework. And so while I've seen a lot of things using softmax functions, I haven't seen anybody on the machine learning literature in my, not extensive but not trivial reading of the literature. I've never seen anybody coming up with these performance bounds on individual test data sequences. So I'd be curious if people know of other references. I'd love to hear it during the discussion. All right, so that's a lot. It's been about 20 minutes, so I was going to pause here if there are questions people want to unload before I finish up with about 15 minutes of showing you some simulations and real data. Any questions, comments, clarifications?
I have a question in regards to slide number 29,
Mhm.
if you don't mind. So here we're still running, we have the problem of choosing what is the maximum number. Is that correct?
That is still true. You have to be willing to, right, you have to make some bet on what's the maximum number we can have.
And when you describe it's unlabeled data, so so the connection with the machine learning, I'm having a hard problem with because when we have a labeled data, we know how to optimize it. But here there is no
Right.
labeled data.
There's no labeled data. So prediction is sort of like a machine learning regression problem where the labels show up one sample after the test data each time.
Test data. Okay.
But for beamforming, we don't have that luxury. If we ever get the labels at all, it's months later after filling out lots of paperwork with the Office of Naval Intelligence.
Okay.
So we're trying to find something that in real time with unlabeled data can still find a performance proxy that says, and you can show this, that given that at least within this competition of this family that are all tuned to look in the same direction, the one with the lowest output power is performing the best, even though we don't know anything about the environment, because we've got this, we began with this constrained optimization problem that led us to the adaptive beamformer. Does that help clear it up?
Yes, thank you.
Other questions? All right, well, I'll use a trick I've learned from teaching online for the last year. I'll put my auctioneer hat on. Going once, going twice. All right, so I'll move forward now to showing the examples. So the first example I want to show you is this is a simulation with a constantly varying number of interferers present. So on this x-axis is the direction. This is time for 1,000 measurements running down or snapshots. And so for people who are used to pass the sonar, this is a sort of a cartoon of a gram. The signal we want is at broadside. So we're going to tune our beam. We're going to pretend we're looking to broadside, and there is a weak signal there at 0. And initially there's one interferer here shown by these other colored lines. The color is coding the intensity. And then for every 100 snapshots though, a new interferer starts showing up, and they're getting louder as they go, right? They're getting more and more yellow and red and orange. And so this is a fairly challenging sonar scenario. We have 20 sensor line array, and we're going to assume that the covariance matrix only gets to average 15 snapshots. So that's not even a full rank matrix. That again puts a premium on things like DMR that can do dimensional reduction in terms of finding the nulls. And so I took this and I went to my beamformer. I ran this algorithm on it for each of the parallel branches, and I'm going to show you the result for each branch, and then also what the blended performance was. So again, this is the DMR dimension. This is the total output power. Each of these circles is a different fixed branch. Basically, one of the parallel branches saying what's the performance coming out of that power. And not surprisingly, because these ones that are assuming there's only 0, 1, 2, 3 interferers eventually have a problem. So they have very high output power, because when we get to be too many interferers, they get overwhelmed and can't keep up. This red dashed line running across is just for comparison. This is where the universal blend ended up. So it's basically actually slightly better than the best one. It's sort of comparable to the best one, but by a half a line width, it's below that. So the universal one with no prior knowledge is doing better than the best fixed one that you would have chosen with hindsight. So this was an encouraging early result for us. And so the question is, well, how are you doing better than the best one in the fixed set? Well, part of the answer is no one of these branches with a fixed number of anticipating a constant number of interferers is ideally suited all the time. Some of them are overestimating and overfitting, some are underestimating. And so let's look at how these blend coefficients evolve over time to get some insight into how the universal algorithm is and this is the doubly adaptive part I should have mentioned earlier, that each of these beamformers within its choice of D is adapting to the data it's seeing to get a set of array vectors, and then we're adapting again among the different beamformers. So there's sort of two levels of adaptive processing going on. And so this figure shows those blend weights, those mu's. This is the time in iterations. This is the DMR dimension, that is, loosely speaking, the number of interferers in the data. And then the vertical in the false perspective is the blend coefficient between 0 and 1. So they all start roughly equally, but when we can see when I get 100 snapshots in, this one here, this is the one that's assumed there's one snapshot. This is the point where one interferer. This is the point where the second interferer shows up, and this very rapidly attenuates because it says, I'm assuming there's one interferer. I can't null two of them. And so I have problems with that. And so my loss goes up, and that softmax function quickly dials this one out of the mix and sort of hands out its share to the other ones. And we see that happen over and over again. Each time a new interferer shows up, eventually it starts to put a lot of its weight on some of the better ones. It really likes 8 here, or likes 8 here in the sort of orangish line for a while, and it's still jumping up until the 9th interferer shows up, and then it just falls off a cliff, and it quickly switches its weights, or if you like, reinvests its beamforming hedge fund on the one that assumes there's 9 interferers, and that seems to be the best option here. So by switching among them and having this ability to adapt that hyperparameter, we get, in this sort of ensemble method approach to beamforming, we can do better than the best of any of these sort of fixed model order solutions. And for those of you that have been around before, they might suspect me of cherry picking my results. I went and ran 1,000 Monte Carlo realizations. So it's not just, I didn't run one and wait till I had a good one to show you. This is 1,000, and over again, the universal does better. This is the same plot I showed you a minute ago, except these are now the mean performance over 1,000 Monte Carlos of the individual branches. And again, the universal mean performance is slightly better. And so in about 70% of those 1,000 trials, the universal one was better than the best fixed DMR. So I'm going to finish because those of you who know Bill Cooperman in the ocean acoustics community may know Cooperman's law, which is simulations are doomed to succeed. And so I wanted to finish by showing you some real data. This is data Kathleen Wage processed that she had from the PhilSea experiment, that when I was showing her some of these results, she said, oh, it would be cool to try it on this data set I have. And so we're going to look at real practical data using the vertical array data from the Philippine Sea experiment. And the sort of footnote star on the experimental part was that the test signal is synthetic injected into the experimental data. So all the noise, background interferers are messy, time-varying real-world things, but so that we could estimate the SNR, we did add, Kathleen, when I say we, I mean Kathleen added a small synthetic signal to the data in a very inconvenient place to see how well the universal beamformer could do. And so for people that aren't familiar with the PhilSea experiment, this was about 10 years ago, and it was a large-scale tomography experiment. There were these 6 T1 through T6 transmitting stations and a vertical line array shown here. This over 5.5 kilometers deep. We're just going to look at this upper subarray of about 30 phones that's near the SOFAR channel that were spaced by about 20 meters. And the data came off in hour-long segments from continuous recordings. And there's a lot of noise in this. There's cable strum, which we used as interferer of opportunity, and then a lot of distant shipping noise as well. The thing that made the strum challenging is that it varies with the current over time. This right panel shows over a sequence of about, about 12 hours. This is a depth versus current profile. So the color in this right plot is the current in centimeters per second. So you see, initially there's some very strong currents at depth due to the tides, but we're going to focus a lot in this interval here because this was very challenging. As the currents died down, the strum was changing a lot with time as it sort of relaxed in these last gasps of tidal current that are showing up here. And so what we'll see in this, I'm going to show you this hour right here. This is a K omega plot. This is time frequency on this axis. This is wave number, vertical wave number on this axis. So this is going up towards the surface, down towards the bottom. The white dashed lines are the visible cone, the cone of where the omega over c that we can have for the wave number. And these dashed black lines show the interference. I'm sorry, show the strum. So I'm going to play this, and you'll see the strum vary a lot along these lines as the yellow is now on this panel. It's the acoustic pressure or the acoustic intensity. And then there's this lighter cone in the middle. This is the distant shipping noise as well. That varies a little bit over time. And so this is a slow animation. You'll see the strum sort of varying in intensity here at different changing frequency and different intensities. And so that's over the course of an hour. There's a lot to adapt there as things are changing. You can see when it goes away or comes back, you can see the shipping noise more. This red dashed line indicates that the location, well, I should mention diagonals in this picture are lines of constant bearing. That as I increase the frequency, the wave number increases proportional to the angle. So something with constant theta shows up in these diagonal lines. We're going to put the weak synthetic signal here because this is about the worst place to have it for this strum, because this means the strum will be right in the side lobe of the conventional beamformer, the peak side lobe. And so you really need a good adaptive beamformer to be able to detect this signal here. And so the parameters, again, it's the 30 element subarray. We'll use 30 snapshots for the DMR thing. That maximum model order size will be 10. This is the sort of convergence hyperparameter that's in the softmax function. And then the other thing Kathleen changed with this was there's a sliding window of 150 samples. And so rather than take the total loss over all time to reflect the fact we know things are changing over time, she had the loss was just calculated over the last 150 snapshots. And so 30 hertz was one of the frequencies where things varied a lot over time. And so I'm going to show you those results first. This is a different way of looking at the blend weights. How do the blend weights look? Well, this is the time in snapshots. This is another coding of that 3D perspective plot I showed you a minute ago. And in hindsight, I like Kathleen's version better, where we go from 0 to 10 interferes, and then the color is coding the mu. So we see initially a lot of the yellow means a lot of heavy weight on things like order 8, 9, early in the thing when the current was very strong. But as the current was dying out over that hour, we see that the preferred dimensions in the beamformer go down to be sometimes 0 or just 1, 2, 3, 4. But a lot of change over that hour. So the beamformer is really changing in response to the environment. This is the output smooth spectrogram, again, over time and a segment of wave number. So you see, this is the distant shipping on axis. These are the strums where, again, you see the variability in these heavy lines, and it's sort of dying down, but then you have these last sort of flickering strums. And then this very light line here is clearly visible, is the synthetic signal coming through. So qualitatively, we could say that weak signal is definitely visible in the spatial spectrogram when we look at the universal beamformer output. The next question is, well, that's nice qualitative. Can we be quantitative about it? So Kathleen went, and knowing the synthetic signal, she computed the SNR of the estimated signal versus the output of the beamformer. And again, the whole way from 10 to 40 hertz. The heavy black line is the universal algorithm, and you can see that's right on top. It's the highest SNR for each of these cases. The others are coding the different branches, the output SNR over time for the different branches. For the low frequencies below 25 hertz, there wasn't as much variability, but the universal still tracked the best one. Right, so we say without any prior assumption or having to put all my eggs in one basket on a fixed model size, I can adapt across this model size and get a better or do as well as the best one. And the next slide shows this zoomed in on the top part so we can see the difference more. When I get above 25 to 30 hertz, you can see there's about a 1 dB improvement. So the universal is better than the best one, from half a dB to 1.5 dB higher, depending on the frequency for these time varying environments. So again, in messy real data that's not Gaussian, not consistent over time, the rank of the interferer is changing. There's a lot of promise here that the universal is doing quite well. All right, so it's 1 o'clock. I'm right on schedule. I'm going to finish here. The main conclusion from this then is by playing this sort of hybrid of adaptive beamforming with machine learning and universal prediction ideas, we can make a universal beamformer that asymptotically converges to perform as well as the Beck's beamformer in this competing family of beamformers by using the performance feedback with the softmax function to change it, if we want to speak machine language, to change the gating functions over time in response to the data to find my new blended set of weights. And that the really remarkable thing is I get this performance guarantee for every sequence that the average per sample performance of my universal algorithm is less than the best beamformer I would have chosen from the parallel branches with 20/20 hindsight, plus a penalty term that goes like order the log of branches over the number of samples, so something that vanishes asymptotically. All right, so I will stop here and open the floor up to discussion and conversation.
Right, Professor Buck, terrific talk there, very interesting. And I can tell you're quite a practiced teacher and pedagogue. Excellent. So
Thank you.
folks, let's, any questions for John? Put me there
I
on
just wanted to say, nice job, John. It's very clever and, you know, very simple, but clearly not obvious.
Yes.
So,
Well, that, coming from you, that means a lot, because I think you are,
yeah.
from your
No,
work in the sort of blended beamformer stuff, you're well positioned to appreciate. What,
Can you talk about the complexity? It seems like there's some, you know, computational efficiencies because you're just basically shifting one eigenvalue from one sum to the other, or is it?
So that's an excellent question. That's a whole nother talk well, not a whole nother talk, but the big picture on universal algorithms. I'll zoom in. I will get your question, Christine. There are two pieces to developing universal algorithms as I've learned more about it and worked on a few other applications of this. Is first to figure out, can you find the right loss function to get it to converge at all? And then how do you make it run in a reasonable amount of time? And so it turns out, like the universal prediction problem that Singer and Fetter did, they were able to exploit the Levinson-Durbin recursion. And so the computational complexity for the universal linear predictor is, in terms of big O, is the same as the largest model you would have used anyways. And using, there's a similar recursion we were able to come up with for DMR that has that same property, that in fact, once I know I want the universal algorithm, I can actually compute the muse and find the universal from the eigenvectors directly. I don't need to compute all these intermediate things. I do need to do some clever recursion things to find the losses to feed to the softmax. But I can get, you know, big O computational complexity comparable, is basically driven by the shared eigen decomposition. The other useful news about that to people that aren't used to thinking about this, that the payoff is that everything I'm talking about here is for one look direction. I would be doing this in parallel for every beam in my passive sonar system, but they can all share the eigenvalue decomposition. So the largest fixed complexity can be shared across all the beams and all the branches. So, I mean, Christine, we can go on more later and I can show you some of the ideas of where the recursion comes from, but I don't want to get that far into the weeds until other people have given up and gone away, if you want to know more.
Thanks, John.
John, a more general question. What kept you motivated to keep at this problem for almost 20 years?
I think it was the idea of the individual sequence convergence. The idea that, the first time I briefed this to my ONR program managers and said, and by the way, I guarantee this beamformer does, mathematically, you can guarantee this convergence property for every data sequence, not average performance, not most of the time. I had their full attention. That idea of saying, now, honesty in advertising, there are data sets where you're just screwed. But what this, none of these may be doing well, but you won't do worse than any of them. I can guarantee that too. So that was some of what, and it's not like, I don't want to give the misimpression. I woke up every day and burned 300 pages of scrap paper or spent the whole day on my terminal. But, in my research time, if not every week, at least a couple times a month, I was trying different approaches to how do I set up the performance, what's the right feedback mechanism, and getting the proof. I even had something that from simulations I was pretty sure the softmax function worked, but it still took me another few months to get all the I's dotted and T's crossed in the proof, even with the sort of cribbing a lot of the approach from the source compression literature. So I think it was just I had a perspective on how valuable this could be in certain passive sonar problems. It was, and this is what tenure is for, right? To let crazy old men chase, high risk, high gain projects like this without worrying about, reporting back on profitability next semester.
Very impressive result in this case. Other questions, please. No, boy, I guess Zarnich is not on here because he's not issuing any reclamas here about being.
Yeah, I figure I'll hear about this from Bob the next time.
Yeah, I was going to compliment you, John, on giving us a new interferer archetype. So this is now going to be a standard scenario, and we may even put it into our interview questions just to test the candidates.
Just to test the people.
Yeah,
it's kind of, I mean, those kind of conceptual questions are good interview questions. Those sort of bank of can you look at a figure and interpret it? Very helpful.
So I got a question for you. If you go back to slide 39.
All right.
And this just basically, there's an interesting pattern in this evolution of your blend coefficients. No, it was in your it was in the simulation before you went to the PhilSea data set. Go right
This
there.
one.
Stop. Yeah. So in the low order cases, D less than 5, or D looks like less than 3, you seem to see this sort of monotonic increase to a max performance when I assume that the actual number of interferers is matching the dimension here, and then a very quick fall off when you're now in an underestimating case where interferers have increased beyond the point of that thing. But in the higher cases, sort of D5 and greater, there's a min that precedes that max. And any intuition on what that is?
Here's what I'm pretty sure what's going on. I haven't completely cemented it, Van, but again, this is just one realization, but I have seen it in others. What that min is associated with this peak. So like where this purple one, it takes a little while to build up enough total output power so that the difference between beamformers shows enough contrast. And so this is getting to the point that the beamformer says, okay, I've got enough difference between 4 and 5 that I'm really sure, or no, this is 3, that 3 is right. So as it goes up, everybody else gets suppressed, right? Because they have to sum to 1. And then, so that's why all these other ones are going down. And then all of a sudden it says, oh no, the 4th interferer showed up. I can't cancel that. And my power wraps up or jumps up, right? And so I feel the pain of that exponential decay. And then the next one sort of jumps up, or the next couple sort of jump up and say, hey, we're all doing pretty good. And just, it is like I didn't design it this carefully initially, but it worked out to be a really good example to say they all get really confident in this moment of hubris right before the interferer shows up and smashes, the new interferer shows up and smashes them down again. So I think that's what's going on with these spikes that are creating the sort of notches in the other ones right before they go away.
Yeah, the reason we had some prior talks in a different branch of AI where you were trying to make some estimate of, how good you're doing based on a very limited data set, and there's some interesting structures that popped out in terms of, sort of false mins and actual maxes, so that you could get led astray on where do I sit on this problem? Am I in the good part of the curve or the bad part of the curve?
Right. Well, is this the one with I think it was Cindy from Duke, the Rashomon?
Yep, that's exactly what I'm thinking of.
Yeah, that was the first one I saw. That was a great talk. She really did. I mean, I've still been thinking about some of those ideas, whether there are beamformer analogs of those as well.
Good. Any other questions from the group? We've had a lot of people here.
There's a question in the chat here from Blake. And this sounds like a Zarnich question, but maybe somebody else can help us out. It says, does anyone know the current NAVC submarine community's metric for the value of 1 dB of sonar performance? How many megabucks per dB? Question mark.
Not a world I live in, but
that sounds like a Zarnich question.
I would ask Zarnich that question if he were here.
No, apparently, I guess nobody can help us in real time here. All right, good
If
question though. But
yeah.
Zornich, I think would have an idea about that. So Blake, ask him.
Well, if it's more than about $250,000, they ONR certainly got their money's worth, because if they can get this into a transition, because and the other thing I should mention maybe quickly is having the benefit of spending forever working on this is I kept a list of related problems that said, if I can get that universal thing going on these sonar problems, here are other related sonar problems. So I didn't want to go on forever today and show more results, but we have done this for the problem of how many snapshots should you average into your covariance matrix, and it works very well.
Okay, great.
As things move. And then my master's student just recently did a version of this using covariance matrix tapering, which is a technique to make the notches wider when you know the interferers are moving, but you don't want to make them any wider than you have to, because again, you're giving away white noise gain. So we have just the most recent ASA meeting, he presented results on a universal version of covariance matrix tapers. So they're just, and we have many other versions of this problem that once you get your head into the universal framework, show a lot of promise.
Sounds like a lot of fun.
Yeah, it is great.
Any other questions? I want to make sure we have looks like, okay, it looks like Bob just trying to answer Blake's question about about processing costs and cost per dB. So John, again, great to see you again. Thank you. I think you have an honor here. You've been a guest of this talk series for a while, and I think you're our first guest that's come back and actually presented. So you're giving back to the community. So thank you for that.
I'm happy to say thank you. It was a difficult spring semester, and I actually really enjoyed the opportunity to, I mean, these were a great seminar, a lot of great conversations. So I'm happy to be able to give something back, because I really did enjoy the times I've attended these. So. And
in impartial honor of that, and also as a way of us saying thank you for giving of your time and walking us through your work, we'll have a swag bag coming your way of all the Metron paraphernalia you could ever desire. But actually, we have more, so you'll just have to give more talks so you get the full bag. You only get a partial set.
I'll get a partial set now. Okay.
Yeah.
I'll have to come back for part 2 when I get the next piece of it done.
But anyway,
excellent. Thank you very much, man.
And thanks for spending some time with us today.
All right, thank you.
All right, John, again, a great talk.
Thank you,
quite a
John,
bit.
and I see Kathleen's also signed in. So
virtual applause
thanks,
for Kathleen, since some of these results were hers.
Hi, everybody. Good to see you.
Hard hat and all. Okay. All right, folks, that terminates the meeting for today. Thank you all for coming.
Thank you.
Hey, thanks, John. Have a great summer.
Thank you. You too, Vad.
Hi, Professor Bach, you going to stop the recording?
Oh, stop the recording? Yep. Find where did I hide the button from myself?
At the bottom.
Hey, John,
Yes.
I didn't say anything, but I thought it was a really good talk.